So welcome to Math 31 Calculus 1 class. My name is Professor Rashidul. A little bit about me. I have 5 bachelor's degrees in 5 different subjects, including one in math, and I also completed a few masters. Currently, I'm working on my doctorate at Columbia University. So here is my email address. So every time you email me, you also CC me at my CC email. This is the calculus book I want you to buy. You can buy any calculus book. The cheapest calculus book you find on the website, because calculus has never changed since the invention of calculus. So before 1665, there was no calculus. 1665, a 23-year-old man was sitting under an apple tree. All of a sudden he saw an apple fall. With the fall of the apple, he started thinking, and he ended up looking at the sky and he saw a moon. And he asked a key question: if the apple falls, does the moon also fall? He wanted to solve that falling apple and falling moon problem. However, the math of 1665 was not advanced enough to allow him to solve that problem. So what did he do? He invented a new branch of math, which we call calculus. And he used the calculus to lay the foundation of physics. So physics, when you talk about physics is built in calculus. So when you learn calculus, you actually learn a branch of math that was used to lay the foundation of physics. Homework 1 is you print the syllabus from online. I already posted it on the website. I did not print it because if I do print it and give it to you, you don't care. You care less. When you print it, you care more. So that's why I want you to print. That's homework 1. Homework 1 is syllabus. Print the syllabus and make it 2 class on Wednesday. Homework 2. Buy a folder. You have to put the folder here. I will collect the folder and I will bring the folder and I will put it here. And every day you come here, you put the homework inside the folder. And when I leave, I take the folder with me. And I will bring the homework either night or on the weekend. Homework 3 is the notebook. I want you to buy a notebook. This is spiral binding notebook or a marble notebook, and first few pages should be empty. So first page you're gonna write just like here. There's a content, so you have to write lecture 1 and then page number. And then homework 4 is the textbook. So you show me the textbook. You bring the textbook to the class, and that is homework 4. Homework 5 will be problem from chapter 1, and homework 6 will be problem from chapter 1.2. So after homework 4 is gonna start getting difficult. One more thing, this is the breakdown of the grade. So the first one is notebook chat, and then homework. There will be at least 20 homework, 19 quiz, 3 exams, and the final. So this course, the calculus course, this is a 4-credit course, and this is very demanding. So my expectation is very high from you. So read the syllabus and sign on the bottom of the syllabus. If you do not agree with the terms and conditions of the syllabus, then drop the course. Now, today we're going to try to understand. Now we'll start the administrative part is over. Now I'm going to go over the algebra for calculus 1, and today we're going to try to understand why the limit of the Fibonacci sequence is golden ratio. The limit of the Fibonacci sequence is golden ratio. That's what we're going to try to understand. Okay, so the Fibonacci sequence Fibonacci sequence, as we said that Fibonacci number, the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The first one is 1. The second one is 1. The third one is 1 plus 1 is 2.
3, 5, 8, 17, 21.
Let's say we're gonna now understand it. Since we already have the hang of it, we're gonna write the recursive formula to derive the 10th. So n is fn minus 1 plus fn minus 2. So number 10, because this is 10, 9, let's do the 9. f9 minus 1 plus f9 minus 2. f9 is equal to f8 plus f7. f9 is how much? f9 is, okay, that's what we're going to find it. f8 is how much?
21.
21 plus
13.
13, and that gives you 34. So this must be 34. Is this 34 if you do that?
Yes.
That makes it recursive because the nth number, which is 9, depend on the sum of previous two. It depends on the previous values. That makes it recursive. So we call it recursive function. Recursive function. There is a mathematical term, and that is a recursive function. Okay, now the Fibonacci sequence, the Fibonacci himself, and I said that he was born 1175 to 1250 in a place in Italy. So fn minus 1 plus fn minus 2 is equal to 1 plus square root of 5 and minus 1 minus the square root of 5 and 2n is square root of 5. So these two statements are same, and then that's what we're going to establish right now. This is our goal. And that would be very algebraically very challenging. So first we're gonna test it for a number. Let's say we're gonna test it for 2. So let's say n is 2. N is 2. If n is 2, what are you gonna get? If n is 2, what are you gonna get? f2 minus 1 plus f2 minus 2 is equal to 1 plus the square root of 5
Over 2.
2
Yeah, 2.
minus 1 minus the square root of 5 2 over what? 2 square the square root of 5. So this is already kind of challenging. Is gonna verify your ability of solving algebraic problem. So 2 minus 1 is what? 1 plus 2 minus 2 is 0 is equal to 1 plus the square root of 5 is square. You probably remember that a plus b square is what? A square plus 2ab plus b square. You have to remember that, so that 1 plus 5 square is 1 square plus 2, 1, 5 plus 5 square. Very good. You have to put minus. You have to be very careful about the sign. Minus. And then you have to write this formula. A minus b square is how much? What is it? Very good. So now obviously this is our A and this is our B. So 1 square minus 2 plus on the bottom, you're almost done. On the bottom you have 4 root 5. 4 root 5. Okay. Does that make sense to everyone? F1 is what? We already made a table somewhere. What is F1?
1.
F1 is 1. So 1 and this is 0. So 1. On the left you have 1. On the right, let's see what do you have? 1 plus 2 root 5 plus 5 minus 1 plus 2 root 5. Not plus, minus 5. Does that make sense to everyone? So 405. Now, I see that 1 cancel and 5 cancel, right? 1 cancel, 5 cancel. So what do you have on the top? Please don't come late. Yeah. Okay. 4 square root of 5 over 4 square root of 5. So 4 square root of 5 over 4 square root of 5 by definition is what? 1 over 1. 1 is equal to 1. What is the Fibonacci number 1? 1. What is the Fibonacci number? 1. So it works for, you check that, right? It works. That formula works. Does that mean you're going to claim that this formula will work for every number without testing every number? No, you're not going to say that. So what are you going to do? You're going to start testing every number? How many numbers there are? Infinite. Can you test all the number? No. So what are you going to do? You're going to have to find a way. Otherwise, if you check it for 200, 2,000, 200,000, 2 million, 20 million, 200 million, 2 billion. There is more than 2 billion, right? So you cannot possibly check all of the number. So you have to find a way. And that is, you're going to say, it works for k. And then it works for k plus 1.
I didn't finish writing. I wanted to copy what you were writing.
That's why I'm taping it.
Oh, okay, all right.
So I put it online.
Okay.
So you can watch it as many times as you need. But I give you more time. Yeah.
I have a favor to ask for you. When you write in the formulas, link them for me like this. When you rotate them like this, I have trouble following you.
Oh, okay. I'll write.
Yeah.
I'll write.
Thank you.
Okay, let me use more space. Yeah, you have to copy that, right? Copy that. Then you probably don't have to. If you understand everything here, you don't have to watch it, because if something you don't understand, you watch it. If you understand everything, you don't need to watch it, because you probably take other classes. Yeah.
Basically, the only thing that we need to get any point in the US is n. Because we already have the formula.
We have few goals. We have few goals doing this one. The first goal is refreshing your algebra. Second goal is testing your algebra to see how much algebra you understand. Okay. Number 3, using algebra to do something there that is very big. And number 4, the main big goal is what you can do by algebra, which takes more than an hour. You can do it by using calculus with less than 10 minutes. But you have to have calculus background. So what did I say like 10 minutes ago? I said that the limit of the Fibonacci sequence is what? Is the golden ratio. What is limit? Is there anyone? Someone said that to calculus before. So what is limit?
Oh, it's you can limit is just when you reach a certain point without going to 0 or a certain
Okay, limit is an approach. Limit is an approach, right? So when you have, I will give you an example maybe on Wednesday, but limit is an approach. For example, 0 over 0, right? 0 over 0 is undefined, right? Okay, I'll give you a nice example on Wednesday who is allow us to approach 0, to solve the problem when this is 0 over 0. So limit, the technique of limit allow us to solve the problem when algebra failed to solve it. Algebra failed to solve 0 over 0 problem because algebra doesn't have the concept of limit. Calculus has a concept of limit. That means you'll never be at 0. You're always going to approach 0 from both sides. From this side, and this side, and this side, and this side. So you can solve the 0 over 0 problem without being at 0. And that is limit. And the limit is very useful concept. Very useful. And if you do struggle understanding limit, don't feel bad. That's how it should be. It takes lots of time to get the hang of limit. Okay, so let's go back. I can erase it now, right? Okay. Let's go back. Okay. So here, so we're gonna make a statement, hypothesis. If it works for number 2, it should work for number k. If it works for 2, it works for k, and k is a real number. K is not a real number, k is a natural number, k is a whole number. You understand the different type of number, right?
Yes.
There are 2 different number, real number and complex number. There are 5 different type of real number. Natural number, whole number, integer, rational number and irrational number. Rational and irrational number. Natural number starts from 1, infinity. Whole number starts from 0, infinity. Integer, just those of you who kind of forgot. Integer, what is integer? Yes.
Negative and positive.
Negative and positive whole number. So yes, the negative infinity to positive infinity. So plus minus 2, plus minus 1, 0, and infinity. Okay. What is the rational number? Anybody?
1 point.
Rational number has a identical ending, right? So what is it? 1/3 is a rational number? Is 1/3 has an identical ending, right? What is 1/3? Very good. So 0.3333 forever. So you just put a bar on it. Makes it rational. Irrational number? Golden ratio is, for example, an example of irrational number. Pi is an example of irrational number because 3.149.
It's an infinity.
Huh? Yes. Yes. Okay, let's go back. So it works for, if it works for 2, it works for k. K means any number. Does that make sense? So now you're going to write it down. So you're going to write 1 plus square root of 5 n minus 1 what? Minus square root of 5 n over 2n plus 2n square root of 5. Now instead of n, you're going to say it works for k. Now you're going to make a big hypothesis. And big hypothesis is if it works for k, it should work for what? To work for k plus 1. Any number. K plus 1 means any number. The next number. K plus 1 is next number. If k is 10, it works for 11. If k is 10 billion, it works for 10 million 1. Does that make sense? K plus 1 capture all the number in the universe. Whole number. Okay. Now we're going to write f k plus 1. Okay. You remember this one? Fn is equal to fn minus 1 plus fn minus 2. You remember that, right?
Yeah.
So give me an equivalent statement. Right now we have to do for k plus 1. What should be a recursive equation for fk plus 1 which is equivalent to this one? Yes? Yeah. What would be the equation for this one? Instead of like, see this is f of k, right? K minus 1, k minus 2. Do you see k here or do you see k plus 1 here? K plus 1. So what should I write here so that this one and this one would be same?
Fk plus Fk
minus 1 plus k minus 1
No.
minus 2
No.
minus 1. Yeah.
If fk plus 1 equals fk minus 2 plus fk.
FK plus
fk plus fk.
Okay, raise hand for this one.
Oh, yeah.
Raise hand for this one. And raise hand for the one you saw before. No one is, because I already raised it, so it gives you some kind of like confidence that this thing
No.
true.
No.
No?
No.
Okay. All right. Yes. Let's. When we do not agree, what do you do? If you math student, your life is easier than if you do something else. Because something else you cannot investigate, right? You argue, and then you fight probably. In math, what do? You prove it. So let's prove it. Okay, give me any number. 9. Okay. K is 9. So F 9 plus 1. F what? 9. Okay, everyone please do that. Plus F
8.
9 minus 1. So you see everything what's going on now, right?
Yes.
So 9 plus 1 is 10 is equal to 9 plus F8. F10, did I erase that or you already, you still see F10?
Yes.
What is F10?
55.
Huh?
55.
5. F9?
Yes. 34.
74? 34?
Uh-huh.
And then? 34?
It's 21.
21. So let's do add. 1 plus 4 is? 2 plus 3 is? 5. Do we have to fight? No. Because it's the math class. You don't have to fight. You can do it by using chalk. If you drop the chalk, you take other one.
You don't take it.
Okay. So yeah, this is the equation which is equivalent. It doesn't look like equivalent, but we already kind of accept that this is equivalent, right?
Yes.
Okay. Because math is not common sense, so it probably don't look like. It probably like physics. Math is not common sense. Physics is also not common sense. When you move fast, you gain weight. If you move faster, you gain weight faster. If you move close to the speed of light, you become like bigger than Empire State Building. Right? Does that make sense? It does not make sense. That's why nobody can move close to speed of light. Because you become so big, it's impossible to move fast when you get bigger. It doesn't make sense, but it's true. Yeah.
Why do you choose to replace n by k? Or you want to say this?
Oh, replace n by k. Yes.
But you could have keep n.
You could have keep n, but we initially use n.
Okay.
We could have used the q. We could have used the p. We could have used something that is different than n, because we started with n. Okay, but it is convention to use k. Yeah. Any other question? So now we understand that it is k plus 1. This is the correct formula. Now we're gonna solve that. And solving this one would be challenging. Okay. So you're gonna write f. What is it now? We now know that fk, then plus f k minus 1 is equal to. First we're gonna we're gonna now deal with that one.
Oh, okay.
First we're gonna put the k term. So 1 plus the square root of 5 k minus 1 minus the square root of 5 k
Over 2k.
2k the square root of 5. Then we're gonna write what?
So
Yes.
instead of k, shouldn't you write k plus 1 because you're using this one for k plus 1?
This one, that one. K plus 1 is equivalent to this one.
Yeah. So why should you use k then?
This is this, and there would be we're gonna have to write.
Oh, so you're gonna
Yeah. Okay. What is this sign? Plus. So we're gonna write plus. Now 1 minus the square root of 5 raised to what? Not k.
No, k plus 1.
K?
Minus 1.
K minus 1. K minus 1. Does that make sense? Because this is equivalent to that. If this is equivalent to that, writing this means writing this. Does that make sense? Algebra. And what is this? K minus 1. What is the sign in the middle? Minus. 1, this is plus, this is minus. K minus 1. So many times. So yeah, if we have a typo, just stop me and fix it.
2k minus 1.
2k minus 1, the square root of 5. Look good?
Yeah, I'm with it.
Yeah.
You said basically what you're doing is fk is this one, and fk minus 1 is
That's
this
right.
one.
So fk,
You're just substituting, right?
yes. You
Yeah.
just substitute the power.
Gotcha.
Okay. This is fk, this is fk minus 1. What is fk plus fk minus 1? K plus 1. Does that make sense?
Mhm.
This is algebra, not
Basically,
calculus.
all of it is f, and the power is then the k
Right.
minus 1 and
Right.
k. Yeah.
They said if you kind of lost.
By now it makes
Like, at the beginning, we have
One or two.
a sum of two expressions give the formula.
That's right.
And the formula is n. Why do you have to have a sum of two expressions?
Because this is equivalent to this. So this equal to this equal to this is the same thing. It looks bigger doesn't mean that it is different than this. It's the same thing. Yes.
You could also put another equal sign hypothetically and write it as that, but with k plus 1 instead, right?
Yeah.
Yeah. That's,
Yeah. That's right. If you don't make it bigger, you cannot solve it.
right.
If k plus 1, what? How can you? For example, proving 1. Proving 1 plus 1 is difficult task because there is nothing much to work. So you have to make it so complicated and come back to 1 equal to 1. Does that make sense? That's why 1 equal to 1 is like 10 page or 11 page proof. It's like because if you don't make it complicated, you do not come back to 1 equal to 1. So much assumption you have to make. Okay. So what are you gonna do now? All right. So you're gonna do some fun now. You have to make a common denominator, which is really challenging. When you have 5 over 2 plus 5 over 3, what is the common denominator?
6. 10. No, wait.
6.
Okay, what is the GCF? Put it another way. What is GCF? GCF is?
Greatest common factor.
Oh, and what is that? 6, right? GCF is 6, right? 6. GCF is 6. Or you can do it this way. 3, 3, 2, 2. So GCF, that makes GCF what? 6, making the same common denominator, right?
Yes.
If you don't like GCF, you make same common denominator, right?
Yes.
That's what you're gonna do. But this is a little bit more challenging. How can you make this guy and this guy look same? You use the algebra. Multiply this is by 2. If you multiply this by 2, what should you do? Top by 2. Okay, we still remember our algebra. You have to multiply this one by, I don't expect you to tell me, but if you can tell me. You multiply this one by what? So that this one and this one same.
Half of it? One half?
Yeah.
No.
1.
No. Yeah.
2k plus 2.
Now, what number you have to multiply this quantity by so that this one and this one is same?
Yes.
Jeffrey.
K by 2?
2k plus 1?
It's a number. 4.
4. Now this one and this one is same. Yes or no? No? Okay, we'll show the proof. No, we don't have to. So 2k square root of 5 is equal to 4. 2k minus 1 is square root of 5. We're going to show that this is the same. So write it down. What is the power? 1. So 2 raised to 1. Is that okay?
Yes.
2 raised to k. And it's square root of 5 is equal to. We have to make the same base. So we have to break it down.
Yes.
2 squared. 2k minus 1 square root of 5. Some of you already see that. What is happening? What is the same base? What is the base?
4.
Not 2. 2. What is this power? 1. What is this power? Do you multiply or do you add? Power you always add. So 1 plus k is square root of 5 is equal to 2 plus k minus 1 root 5. So what do you do? 2 k plus 1. Remember, this is community property. You can put k at the beginning. You can change the order. Does that make sense?
Yes.
Because order doesn't matter. So 2k plus 1 square root of 5 is equal to what? 2
K plus 1.
k plus 1
Square root of 5.
square root of 5. So then this and this is same. Okay, but you're gonna forget it if you don't write it down. Okay, so we have the common denominator, and that's a good thing. Okay, can I erase it?
No.
Okay, sure. Yeah. Okay, so, yeah. So we have the same downstairs. So what is our same downstairs? 2 raised to k plus 1 root 5, right? We have the same base, right? We have the same common denominator, right? Now what are you going to do? We're going to distribute that. That part is easy. So 1 plus root 5k minus 2, 1 minus root 5k plus 4, 1 plus root 5k minus 1 minus 1 minus root 5k minus 1. That is 4 here. That part is easy, right? Okay, now we have to do some thinking. This is 1 plus 5, right? Is there any 1 plus 5 do you see? 1 plus root 5. Is there any 1 plus root 5 you see? Which one? No, this one. So, is there any 1 minus root 5 you see? Put something different than that. Okay, so we have to use that algebraic manipulation in a very creative way so that we can accomplish our goal. Okay, so we have to write this guy. Can you write 4 without writing 4?
2 square.
Very good. So you can write 4 without writing 4, right? Can you write 2, this quantity, without writing this one?
That quantity without writing?
Without writing it. It's not going to be as easy as like writing 4 without writing 4. Maybe it's easy. Yeah. So 2, 1 plus root 5, 1 plus root 5, k minus 1. So I'm claiming that 2, 1 plus root 5, k is equal to 2, 1 plus root 5, 1 plus root 5, k minus 1. It's the same thing. Should I show you or you accept it?
Sure.
Okay, so show 2, 1 plus root 5, k is equal to, what is the common base? 1 plus root 5, right? So 2, 1 plus root 5. What is the power here? If you don't see the power, 1. 1 plus k minus 1 plus 1 cancel. So it's the same. Okay? So now, is that fine? Is that fine? So, is writing 4 equal to 2 squared? Or writing 4 equal to 100 minus 96? Does that make sense? 4 equal to 100 minus 96. Is that okay? Same thing, right? So it's the same thing.
Basically, you write the same thing without writing the same thing.
Yes, without writing the same thing. That's correct. Now, what is the next one you have to write next to it? 1 plus root 5. Where is 1 plus root 5? This guy. So pull it out. Here, plus 4, 1 plus root 5, k minus 1. What is left remaining on the office stairs? This guy is remaining and this guy is remaining. You have to break it down in two parts. So we're going to do it same way.
The same thing.
Minus 2, what are you going to write?
1 minus square root of 5.
1 minus root 5.
1 plus square root of 5.
1 minus root 5.
5.
K minus
K minus
1. Does that make sense? What is remaining? We wrote everything else except one thing. What is that?
4 1 square root of 5. K
Minus
minus 1.
4 1 minus root 5 k minus 1. K plus 1 root 5. Okay. Now we're gonna have to write it here. Okay. So now what is gonna be here? Can someone help me copy that? 2
1 plus
1
square
plus
root of
5.
1 plus square root of 5 k minus 1 plus 4 1 square root of 5 k minus 1 minus 2 1 minus square root of 5 1 minus square root of 5 k minus 1 minus 4 1 square root of 5 k minus 1 square root of 5 k minus 1
Okay.
over.
I promise that was the most that we done with the difficult part. What is that?
2k
2k plus
1 square root of 5.
square root of 5. Okay. All right. So now what is the common factor? We know common factor, right? 4x plus 20y. What is the common factor between these two guys?
4.
4. No, not 5. 4. 4 is the common factor, right? X plus 5y, right? Okay, this is obvious. This is not obvious. So what is the common factor? 1 plus root 5 k minus 1. Very good. That's the common factor. Okay, now I'm going to write 2 plus 2 root 5 plus 4. Is that okay? 2 root 5 4.
Now,
Yeah. Does that make sense? I factor out that one. So if you multiply, okay, another way of saying the same thing. If you multiply this one and this one, you're going to get this one. Does that make sense? Okay. All right. Minus 1 minus the square root of 5 k minus 1. Then you want to write 2
1
okay, minus what is it?
minus 2 square root of 5
2 is square root of 5
minus 4
plus 4.
plus 4.
If you multiply this one and this one, you're going to get top. Don't forget the bottom. What are you going to get on the bottom?
Basically, what you're doing is dividing in 2.
Yeah, if you multiply that, you're going to get that.
Like the common factor of this part and then the common factor of this part. You're dividing in 2 parts.
Yeah, 2 part. Yes, that's right. When you do the trinomial, solve the trinomial x squared plus 2x plus 1, you get a final answer that look like what?
And 2 different.
I'm sorry, where is coming from the plus 4? I thought it's minus 4. Sorry.
Minus, you distribute the negative sign. Once.
But it's the last block. It's minus 1.
This minus and this minus.
It's minus. The divided by
Minus minus is plus. Okay. So what are you going to do now? You're going to write 1 plus square root of 5 k minus 1, 1 plus 2 5 plus 5 minus 1 minus square root of 5 k minus 1, 1 minus 2 root 5 plus 5. Is that okay if you write that? No, divide, I will write that down in a second, but do you understand that? 1, another 1 move to over here. Does that make sense? You write 1, right?
Yeah.
1 plus 1.
Yeah.
So then 1, does that make sense?
Yes.
Okay. Why did you do that? We'll figure that out in a second. Okay. So divide by what? Divide by
2k plus 1.
2k plus 1 is square root of 5. Now what are you going to do? 1 plus square root of 5, k minus 1, 1 plus square root of 5 is square. Very good. That's why you did that. 1 plus square root of 5 is square. You work hard to do something and that's what you did. 1 plus square root of 5 and that is a plus b square. Right? This is a plus b square. Minus 1 minus square root of 5, k minus 1, a minus b square. Everything over what? 2k plus 1 square root of 5. Now what are you going to do?
Cancel it.
No. No, you're not going to cancel. Why you have to cancel? This is same base and this is same base. When you have the same base, you're going to be using this one forever. AM is what? N plus M. So you're going to use that rule now. Not that you used that before. So what are you going to do? 1 plus square root of 5, then what? K minus 1 plus 2. Plus 2, right? Plus 2, right?
Still k minus 1.
Minus 1 plus 2.
Yeah, k minus 1 plus 2. And then what? Minus 1 minus 5, k minus 1 plus 2. Over what?
2k plus 1 square root.
2k plus 1 root 5.
Wait.
It looks like it's coming down into it.
No, it's gonna be the same thing, the same base.
So k minus 1 plus 2 is what? I'm not going to write another line.
K plus 1.
K plus?
K plus 1.
K plus 1. Minus, what is this one?
K plus 1.
K plus 1. Okay, so you proved that, right? That's what we started with, right?
Yes.
That it works for k plus 1 and now that's exactly what you get. So what is the limit of this one? The limit, without using calculus, we're going to use the algebra to show that the limit of this one is, the limit of this is what? Golden ratio. Golden ratio. Okay, so the limit of this one, which we will do like 3 months from today, we will do the limit of this one by using calculus. Now we're going to use the algebra to show that limit of this one is golden ratio. Okay, so the limit of this one is, okay, so this is longer line and this is a shorter line. You call it A, you call it B. So the limit of Fibonacci sequence is the golden ratio. So A in algebraic way, writing down is A over B is equal to A plus B over A. A over B is P. This is a Greek word which is P. So A over B is equal to A over A plus B over A. A over B is what? P. Is equal to A over A is 1 plus B over A. If A over B is P, 1 over P. This already looked like a quadratic equation, right? How can we make it quadratic equation? Something we know, yeah. Can we do that? We can multiply everything by p, right? So what are you gonna get on the left?
P squared.
P squared p plus 1. In order to make it a quadratic equation, you have to set it to the 0. Set it to 0. So p squared minus p minus 1 is equal to 0. Now, the quadratic equation is the Fibonacci and golden ratio touches every single branches of algebra. Now we are touching the quadratic formula. Minus b plus minus b squared minus 4 over 2a. Our a is 1, our b is minus 1, our c is minus 1. So what is our b? Minus 1 plus minus 1 squared minus 4, 1 minus 1, 2, 1, right? Oh, okay, very good, yeah, very good, yeah. Otherwise we will not probably get a real root, yeah, very good. So, plus 1 plus minus 1 plus what? 4 over 2. So it has like how many root? 2 root. So one is 1 plus is root 5 over 2 and the other one is 1 minus root 5 over 2. This is golden ratio, this is extraneous root. This is the extraneous root.
The negative one is extraneous root?
This is not negative, this is just, this one is extraneous root. Extraneous root, how many of you know extraneous root? Raise hand. Extraneous root is not valid. Answer, that is not valid. For example, time cannot be negative, size cannot be negative, height cannot be negative. When you deal with physics, lots of extraneous root. The quadratic function always gives you two answers. One is the valid, one is not valid. At least not today. Maybe it would valid when we can go back to time and meet our grandma. Yeah. Okay. So 1 plus the square root of 5 over 2 is 1.6. And this is golden ratio. Okay, and the limit by algebra, now we're going to make a connection between the Fibonacci sequence. You didn't probably see the connection. Now we're going to see the connection.
So this demonstration is for golden ratio.
Basically, the golden ratio is the final.
This is the golden ratio.
That you can do anything then.
The golden ratio, yeah.
The final answer.
What do you mean?
The golden ratio is your final solution, the final solution. That you can do anything else.
The golden ratio is a number that captures the essence of the mysterious nature that we always try to understand. Just like a physics equation, just like the size of electron. The mass of electron is 9.11 times 10 raised to negative 31. Why it is not negative 33? Why it is not negative 30? Why it is exactly negative 31? We try to understand that. So the golden ratio is one of the most mysterious thing. Why it is most important constant that hidden in nature, and that math allow us to discover that. It always hidden in the nature, and math allow us to discover that. So the golden ratio is one of the kind of most mysterious, one of the kind of most important number, a constant that was hidden in the nature for many years, and Fibonacci sequence allow us to kind of discover that. So we're gonna use that ratio now. So A over B is what? A over B is we're gonna write A plus AB is equal to A over B. Give me some Fibonacci numbers, Fibonacci sequence now. 1, 1, 2, 3, 5, 8, 13, 21, 34. Okay. Let's say A is 2, B is 3. Then it is B over A. The formula is B over A. Ratio is B over A. So 3 over 2. 3 over 2 is 1.5. You will see that the limit of the Fibonacci sequence is the golden ratio. 1, and then 2. You get some idea. 1, 2, and then what? 1, 1, 2. Did you put 2 up or down last time? Up.
You put it down.
I put down. Okay. Okay, and then 3. Which way 3 should be? And then 5. Which way 5 should be? And then what?
Then
8. Which way 8 should be?
left.
And then 13. And then
Right.
21. Hopefully this time we are right. Okay. So this one.
Yeah.
This is called Fibonacci square. Our head, the human head is Fibonacci square. Plus 2, plus 3, we know the next number, right? So plus, what is the last number? Why it have to be 100? Can it be 1 billion? Why it have to be 1 billion? Can it be 1 trillion?
It can be any number.
Okay, so that's better, right? It can be any number, right? Is equal to what we said? Is equal to n plus 1 over 2. That's what we said, right? So we are testing our machine, right? We are testing our machine that this equal to that. Okay, let's do test our machine. Before we said if it works for 1, then if it works for 1, if it works
For 1 or for k.
for 1, it will work for
Okay, k is any number.
for k. Okay, so let's see whether it works for 1. Okay, so the first one is 1. 1 is equal to n, no, 1 plus 1 over 2. So 1 is equal to 1, 2 over 2. So 1 is equal to 2 over 2. So 1 is equal to 1. So it works for 1. Writing it down because you, whatever you do in the class, you should have that because you are responsible. It works for 1. So if it works for 1, it should work for what?
For any number.
We're not gonna test all the number. It should work for k, right? That's the math approach. It works for k. Okay, so we're gonna say it works for k. It works for k. If we say it works for k, we have job to do, right? We have things to do, right? So we're gonna write 1 plus 2 plus 3 plus k, right? Is equal to k plus 1 over what? 2, right? Now we're gonna do the same thing. Since it worked for k, it should work for? No. K plus, who said that? Okay, it worked for k plus 1. It worked for k plus 1. Okay, let's see it worked for k plus 1. So we're gonna write 1 plus 2. You tell me what to write. Plus k plus. Is that okay on the left side? The left side look fine. This is much simpler than the one we did before. The one we did before touches every part of algebra. This one does not. What are we gonna write now? Every time you see k, you write k plus?
K plus 1.
Okay, so k plus 1. K plus 1 plus 1 over 2. Is that okay now? Then this part is kind of not obvious, but it's gonna become obvious. Instead of writing this, what can you write?
K multiplied by k plus 1 over 2.
Very good, very good. K plus 1 over 2. Very good. Very good. I'm glad that you see that.
Say right.
Is that okay with everyone? That instead of this, we wrote this. Is that okay?
Yes.
Okay. All right. It's like writing 4 without writing 4. Okay. Yeah. Plus k plus 1 is equal to what? K plus 1. Then what?
K plus 1 plus 1.
No.
Like,
K plus 2 over 10. Now either we have to make the left side equal to right side or right side equal to left side. Which one looks Okay, let's make left side equal to right side because right side looks already almost simplified. Does that make sense? As soon as we make the left side equal to right side, our job is done. What is common? Again, what is GCF? 2. Okay. 2. Tell me what is on the top. K plus 1 plus 2, K plus 1. Is that okay? Is equal to that. Is equal to that. Now you probably see what I see.
Yeah.
What do you have on the left side? K plus 1, K plus 2 over. This is exactly that. So then this is, now we're going to say that this is, no, we're going to say this is the machine for this one. And we call it a formula. We don't call it in math, we call it formula. Just like machine. So this is a machine for this. Yes?
So you can use the K plus 1 to solve most of the formulas?
You can use?
K
Not most of the all.
all of
K
them?
plus 1, yeah. K plus 1 means any number.